So we're going to introduce magnetism now, and the first part we're going to be talking about is what magnetism is, and we're going to talk about the magnetic force that results from moving charges. So here's a magnet. It has a north and a south pole. There is notably no monopole. You won't find just like a north pole floating around. It's always coming in pairs there. And just like we might expect, like poles repel, and unlike poles, opposite poles, attract. Okay, so nothing really new there. Magnetic force can clearly operate across a space, so there is a field involved. There's the field. It goes from north to south. And the magnetic field, which we're going to start calling the B field, the magnetic field lines go from north to south, and the field is measured in Teslas. 1T, capital T, equals 1 Newton per ampere meter. Wow. So here's a situation where charge is moving through a B field. The B field is pointing up, and this charge will end up experiencing a force. So static electric charges cause E fields and forces. We're not really talking about this here, but moving electric charges cause B fields. I'm not going to illustrate that. But very importantly, B fields exert a force only on moving charges. Okay, so in this case, this Q is moving along. We assume it's a positive charge, moving with a velocity v. And the expression that we have for this is FB, which is really the magnetic force, is equal to the charge times V cross B. So we've got to use the right-hand rule to find the direction. The numbers aren't that bad, right? QV cross B is just going to be Q times V times B times the sine of the angle in between them. But we're going to have to use the right-hand rule to figure out the direction of the force. Well, if you take V and B, the way I do it is I point my fingers in the right hand in the direction of V and I curl them in the direction of B. Then my thumb will point out of the screen, which we represent with a dot. You're going to see a lot of that. In this unit, there's a whole lot of right-hand rule. There's a whole lot of three-dimensional stuff. The other way people do it is they take the first finger, point it in the direction of the V, take their second finger, point it in the direction of the B, and their thumb theoretically points in the direction of the force. The force is always going to be perpendicular to the VB plane, always going to be perpendicular. So it's either going to be coming out of the screen or into the screen in this situation. Now here's what's kind of important. There's the equation. Some important aspects. The force is given by the right-hand rule, and it's always perpendicular to V and to B. So if you take the VB plane, the plane that those two vectors lie in, we're always going to be perpendicular to that. V is always going to be, V in the same direction as B always results in no force. So in other words, if V and B are parallel, there's no force on there. Okay, it's really VB sine of 0, right? So there's no magnetic force if it's traveling in the same direction as B. It's only the part perpendicular to B that results in a force. So we'll look at first off on this. There's V, there's B. The B's are all to the right. The V is up at an angle of 30 degrees. The plane of B and V is the plane of the screen, so the force is obviously going to be either out of the screen or into the screen. We'll look at that in a second. We have a Q, we have a V, we have a B. QV cross B. And now we've got sine of 30 in there, so it's QVB sine 30. So the magnitude ends up being 0.48 newtons when we plug all those numbers in. The direction, if we take two different ways, if we take V and rotate it into the vector B with our right hand fingers, our thumb will be pointing into the screen, which is represented by an X without a parentheses at the end. The other way is point index finger in the direction of V, second finger in the direction of B, and your thumb points. Again, either way you do it, it's going to be into the page. How will a negative charge move in this case? And I'm not even talking about here instantly. I'm talking about how will it move continuously. And it's a really interesting thing that underlies things like mass spectrometers, which we'll look at later. So the B field is these X's. That means it's into the page. Think of an arrow going away from you and you're looking at the feathers when it's coming towards you, coming out of the page, we look at it as dot. Think of it as an arrow coming towards you where you're just seeing the tip. Okay, so first of all, let's worry about the direction of the force at that instant. Okay, so if it were a positive charge, I'd take my fingers, push them to the right, fold them into the screen, and my thumb would point up, perpendicular to the BV plane. So the force would be up. But this is a negative charge, so it's in the other direction. So that's the direction of my force. So that's nice. Now what's going to happen is that force is going to make that charge curve a little bit, right? Now let's take a look at this new spot, and we take the V and we rotate it in the direction of the B. My thumb would be pointing kind of up to the right, but it's a negative charge, so we use down to the left, like that. And this is really, if you think of it, the V and the B are always perpendicular, so there's no change in that sign of the angle. Q, V, and B, the values don't change, so that force will be constant, even though that arrow looks a little longer. The force will be constant. It'll be towards the center. This is circular motion, uniform circular motion. Let's take this one. Same sort of situation, except now we have a positive charge. And they say, what must the velocity be so the charge is undeflected? No gravity. Okay, so we're not doing a vertical thing. But we have E field down, we have B field into. Okay, so we're really instinctively, we're going to say the E field force is going to have to be equal to the B field force. The E field force is definitely going to be down, right? Okay, and the B field force, V cross B, you're going to find your thumb is pointing up. So the B field force is going to be up at QVB sine of 90. And that has to equal the E field force, which is Q times the E field. And when we solve that, the Q's cancel. We end up V equals 4 times 10 to the 4th meters per second. That's how fast it's going to move. Any slower, and it's going to curve downwards because the E field will dominate. Any faster, it's going to curve upwards because the B field will dominate.